Hello everyone, we are ME44 and over the past year we have been studying the effects of geometric and mass imbalance on rotor assemblies. Our faculty advisor is Dr. Nejat Olgag and our project sponsor is Dr. John Wong at Pratt & Whitney. The goal for our project was to design a test rig that can be used to isolate and identify the force effects of geometric and mass imbalance on a rotating assembly. Geometric imbalance is the deviation of the neutral axis from the bearing center line at rest. Mass imbalance is the deviation of the center of mass from the neutral axis. If a system is subject to both of these imbalances and is rotating about both these axes at the same time, it is said to be whirling. The motivation for this project is a phenomenon named bowed rotor start, in which the thermal gradient of an engine causes the rotor to bend. The rotors are subject to geometric and mass imbalances when this happens. The test rig we designed is essentially a shaft and disc system between two bearings and driven by a motor on one side. The shaft is made up of pieces connected by universal joints that will allow for rotation about both the neutral axis and the bearing center line. The bearing that is not connected to the motor is free to slide along a track such that a prescribed amount of geometric imbalance can be generated. The shaft stiffness is induced via the carriage handbrake. The sensors implemented into the design include a displacement sensor to observe the amount of geometric displacement that the system undergoes, and also two load cells embedded into the bearings to record the resulting forces. The extent of our experimental procedure involves three tests. The first test aims to determine the force effects of a purely mass imbalanced system. This means that both bearing supports are fixed in place and the kink angle along the shaft is equal to 0 degrees. The second test isolates geometric imbalance by including a kink angle in the shaft and fixing the sliding support with the handbrake. This should allow the rotor to rotate solely about its neutral axis while still being displaced from the bearing center line. During the third test, the rig is operated with both a mass and geometric imbalance to observe whirling and gather data on its dynamic behaviors and force effects. Validation of the rig's design stems from comparing data with the theoretical model. We know that as angular velocity increases, geometric imbalance is constant, while mass imbalance increases quadratically. The intersection point between these two curves is the critical speed of the rig. By comparing experimental data to the theoretical trends, insight into the validity of the rig is provided. 3 risks were identified following the critical design review. The first being the displacement sensor not being able to register the motion of the sliding cart. However, if the sliding cart is machined with steel, the maximum distance measurable is 3 centimeters, which is more than sufficient for our rig. A larger concern, however, is pre-existing mass imbalance due to asymmetric assembly, resulting in universal joint failure. Since the pre-existing mass imbalance was a major concern in our design, the team studied the effect of mass imbalance in our geometry. The configuration of our assembly is theoretically balanced, however we expect there to be some center of mass deviation from the spinning axis due to machining error. The plot shown depicts force versus rotation speed for 3 eccentricity values. The largest value of 0.05 was chosen to show a large deviation in the center of mass, implying that the center of mass is located at the edge of the universal joint. The mass imbalance, of course, can extend past this limit, but it was determined to be highly unlikely. Rig failure from the cyclic force would occur at the universal joints, however the joints are rated for 6,000 RPM. The team has reached out to the manufacturer for more information on the universal joint specific to cyclic forces. There was also concern for the disc both not being able to register a controllable amount of imbalance, along with it inducing too much imbalance force. From knowing the lower and upper limits of our configurable imbalance, a range for imbalance forces was determined. When the pins are relocated to the max position, the center of mass is deviated by 0.02 inches. The lower limit results in a deviation of 0.002 inches. This range lies within the safe load limits of our load cell, along with allowing for the force to be measurable. 2 machining tasks remain before assembly can begin, and these include the sliding side load cell housing and cutting the shafts to length. The sensors and the motor must be connected to the controller box. A program in LabVIEW must be created to measure the forces, displacement, and control the motor speed.